So the oxymercuration reaction for alkenes is another way to make alcohols. And it's a reaction that goes very well along with the acid catalyzed hydration. So if you recall, the acid catalyzed hydration, where we used acid and water at high temperature, converted our alkene into a Markovnikov or more substituted alcohol. The problem with this reaction is it requires both strong acid as well as high temperature. And that means that with a large number of other functional groups, this reaction is not very compatible. So the oxymercuration reaction, and this reaction has been around at least since the 1950s when Henbest published it. Uses mercury acetate along with water, and then in a second step uses sodium borohydride to get us to the exact same product. The main advantage of this reaction, though, is clearly the fact that we don't have the same harsh conditions that we do in the acid catalyzed reaction. So next we'll take a look at the mechanism. So the first piece of this mechanism is that the mercury acetate will dissociate. And it's then this positively charged mercury which gets attacked by the alkene. And that gives us a three-membered ring containing the mercury. At this point, water will attack. And the reason water is able to attack is three-membered rings are generally unstable. They suffer from a high degree of ring strain. And in addition, they have this one has a positive charge in it. So the nucleophile here, the water, will actually attack at the more substituted carbon, and that's because that more substituted carbon is able to bear more of the positive charge. That opens up the three-membered ring like this, and we end up now with the oxygen on the more substituted carbon. That oxygen then very quickly loses a proton to become the alcohol. This is where our second reagent, the sodium borohydride, comes in. And this is the point where we would add it. And the sodium borohydride will replace the mercury group with a hydrogen. Now, we're not going to go through a mechanism for this last piece because it turns out the mechanism for this step is not very well known and not very well understood at this point. But in addition to making alcohols with oxymercuration, there's also a second thing we can do. And that is if instead of using water for the reaction, what if we use an alcohol, such as ethanol? Well, most of the reaction mechanism is the same. But when we get to the point where we want to open up this three-membered ring, remember this is the step that makes the alcohol. And the reason it made an alcohol was because we had water to function as our nucleophile. Well, now there's no water present. Instead, we have ethanol. And so ethanol can also function as the nucleophile to open up the three-membered ring. That group will also lose a hydrogen. And then after sodium borohydride replaces our mercury group with a hydrogen, notice that what we end up with here is not actually an alcohol anymore, but we've actually made an ether in this case. So the oxymercuration reaction gives us some options. It's going to add that oxygen group at the more substituted position. But we have some diversity with products in that if we use water as our nucleophile, we get an alcohol. But if we use an alcohol as our nucleophile, we end up with an ether. And so for any starting alkene that we use, we'll just look at the regular oxymercuration with water here. But you could imagine either one of these examples using an alcohol instead. Again, what we'll end up with is the alcohol at the more substituted carbon of the starting alkene. So we'll finish this video off by showing an application of this reaction. And this application is going to be one where this reaction is used in a synthesis. In this case, we're going to not use water, but we're going to use methanol. So we're making an ether. And specifically, again, this is our alkene that's reacting, and so the reaction will take place at the more substituted carbon. That's where we'll make our ether. So our product has this O-methyl from the methanol. From here, this undergoes a couple of additional reactions, and you'll notice the left half of the molecule stays intact. But on the right, we've added an additional piece to it. Went where that was. And what we've made is actually the active component in frontline. Frontline being the what most people will use on their pets to treat for things like fleas. And this is its active ingredient. And this methoxy group over here, this ether piece, can be made through an oxymercuration reaction.